open the latest tech news, you must have been frantically bombarded by these words: solid-state battery. From traditional auto giants to startup battery unicorns, everyone is painting a rosy picture, telling you this is the ultimate salvation for electric vehicles. It is the holy grail of the battery world. The overwhelming propaganda in the media all claims solid-state batteries double the energy density and are absolutely safe and will never catch fire. Does this perfect facade make you feel like we are about to enter a sci-fi, zero-risk EV era? But today, right here, I'm going to ruthlessly burst this perfect pink bubble. Who said solid-state batteries won't burn? You heard it right. Solid-state batteries can still short-circuit, even under extreme conditions. The catastrophic thermal runaway triggers it is no less violent than current liquid batteries. This is the fatal Achilles heel behind this mainstream technology claiming to be perfect. In today's video, we won't talk about those ethereal marketing pitches. We'll directly tear open the packaging of solid-state batteries and dive into the atomic-level microscopic world. I will uncover the truest physical underlying logic of solid-state batteries for you. Logic. And tell you, in order to tame this seemingly docile but actually ferocious beast, what kind of engineering nightmare the world's top engineers are going through. After watching this video, your understanding of battery technology will thoroughly pull ahead of the general public by a whole dimension. Alright, before we pull solid-state batteries off their pedestal, we must first take stock of the products of the Stone Age, which are the traditional liquid lithium-ion batteries, packed inside the bellies of the EVs running all over the streets today. We first need to understand why current batteries are so prone to losing their temper. The operating principle of traditional lithium batteries is actually very simple. You can imagine it as a swimming pool. The two ends of the swimming pool are the positive and negative electrodes respectively, and the water filling the entire pool is the liquid electrolyte. When you charge, lithium ions are like a group of swimmers, jumping into the water from the positive electrode, swimming hard towards the negative electrode. When discharging, they swim back to prevent the positive and negative electrodes, these two sworn enemies, from touching each other and causing a short circuit. A net is also pulled across the middle of the swimming pool. This net is called a separator. Sounds perfect, right? But there is a huge physical limitation and contradiction hidden here. To make lithium ions swim fast enough, we must use low viscosity, high dielectric constant organic solvents as the electrolyte. But here's the problem: the chemical properties of these organic solvents. Frankly speaking, they are no different from gasoline. They are highly flammable and very unstable. When your car is in a severe collision or inside the battery, for some reason, tiny metal burrs are generated, which we called lithium dendrites. When this burr pierces the thin separator in the middle, the positive and negative electrodes contact instantly. At this time, the ruthless punishment of physics arrives. A massive current erupts instantly at the micron-level contact point, generating extreme high temperatures. This high temperature will instantly causing the surrounding gasoline-like liquid electrolyte to boil and vaporize, generating a large amount of flammable gas that bursts the battery casings. Then it meets the oxygen outside, or the oxygen released by the cathode material itself under high temperature. Heat, combustibles, oxygen, the three elements of combustion are gathered instantly. Boom! This is the thermal runaway we often hear about. This is a dead knot in physics. As long as you still rely on liquid organic electrolytes, you will never be able to. Overcoming the contradictory barrier between energy density and ultimate safety. When engineers want to cram more energy into the battery and using more radical materials, the battery becomes more sensitive. This makes us realize that tinkering is no longer useful. The underlying architecture really has to change. Thus, we welcome today's protagonist. The black tech claimed to bring a dimensional strike: solid-state batteries. The core conversion logic of solid-state batteries, if explained in the simplest and most straightforward way, is to drain the water in the swimming pool and replace it with a solid, hard brick. This brick is the solid-state electrolyte. It can be ceramics, such as oxides or sulfides, or it could be a polymer. Now, lithium ions can no longer swim in water. They must move through the gaps of this solid lattice, like ninjas, accurately teleporting and jumping over one by one. This seemingly simple replacement brings what kind of decisive advantage? First, this solid brick itself is non-flammable. It completely eliminates the biggest powder keg inside the battery. Second, this brick is very hard. It can simultaneously serve as both the electrolyte and the separator. This means we can use physical defense to block those lithium dendrites attempting to pierce the battery. Third, because there are no longer the constraints of flammable liquids, we can finally replace the anode with extremely high energy density, pure lithium metal, directly doubling the battery's range. This sounds like a flawless dimensional strike, right? Absolute safety combined with absolute performance. But at this time, a thinking audience will definitely raise questions. Since solid-state batteries are so good and the physical logic is so perfect, why didn't we use them before? Why is it that even now, not a single mass-produced, all solid-state battery-equipped, affordable cars can be bought yet? This leads us to the fourth segment, crossing the engineering nightmare. Everyone, theoretical physics is full of promise, but engineering reality is extremely harsh. Past technical bottlenecks could be described as a disaster. Let's recall the swimming pool from earlier. Liquid has an irreplaceable advantage called wettability. Liquid can ubiquitously penetrate into every tiny pore of the positive and negative electrode materials, ensuring that lithium ions can easily enter the water from any corner. But what about solid states? When you forcibly press a solid electrolyte onto the solid positive and negative electrode materials, this is called solid-solid contact. You can imagine pressing two seemingly smooth stones together, but under an electron microscope magnified 10,000 times. The surfaces of these two stones are actually endless peaks and valleys. This causes the internal structure of the solid-state battery, the actual contact area that allows lithium ions to pass through, to be pitifully small. This extremely poor contact will create immense interfacial impedance once the internal resistance of the battery spikes. Never mind driving a 2-ton electric vehicle. Even charging and discharging might generate extremely high waste heat, rendering the battery completely useless. This is the fundamental reason why over the past few decades, solid-state batteries could only stay in the laboratory. So, how did the breakthroughs in modern technology break this seal? This requires demonstrating the violent aesthetics of mechanical engineering and material science. To make these two stones fit perfectly, modern engineers brought out the heavy weapons of automation and precision machining. We no longer just casually press two solids together, but through isostatic pressing technology, under the extreme pressure of hundreds of atmospheres, forcefully pressing the solid electrolyte into the gaps of the electrodes. Alternatively, scientists invented in situ solidification technology. First, liquid monomers are injected to penetrate, and then, through heating or light exposure, causing it to freeze and solidify inside the battery. Through this almost crazy cross-disciplinary stacking of technologies, we finally barely overcame the engineering nightmare of interfacial contact. Okay, problem solved. Energy density has increased, and the liquid has been drained. Solid-state batteries can finally confidently guarantee they will absolutely not catch fire? Wrong. Dead wrong. This is the climax of the whole video. Get ready to face our most difficult challenges today. confronting the ultimate boss of solid-state batteries. As we mentioned earlier, the biggest gimmick of solid-state batteries is using the hard-solid electrolyte to physically block the growth of lithium dendrites and prevent short circuits. The picture everyone imagines is soft lithium metal crashing into hard ceramics, shattering like an egg hitting a rock. But the workings of nature and physics are far more treacherous than we imagined. This is the biggest challenge that comes with new technology. During repeated charging and discharging under extreme conditions, scientists saw a chilling picture under the microscope: lithium dendrites. This seemingly soft metal acts like a plant's root system, forcibly bursting through the hard ceramic electrolyte. Why does this happen? Because although ceramic is hard, it is very brittle. And during the sintering process of ceramic materials, internally, it inevitably creates micron-level or even nano-level grain boundaries and microcracks. When a powerful current drives lithium ions to deposit on the anode, if stress concentration occurs locally, lithium metal will follow these invisible ceramic microcracks and drilling into them. You can imagine a tree growing in a crack in a concrete floor. As the tree roots slowly thicken, the mechanical stress generated by its growth is strong enough to overturn the entire concrete slab. The destructive power of lithium dendrites in solid electrolytes is the same. When the local hydrostatic stress exceeds the fracture toughness of the ceramic material, the microcracks will instantly expand. Lithium dendrites drive straight in, piercing through the solid electrolyte. Once pierced and a short circuit occurs, the real disaster strikes. Although the solid electrolyte itself does not burn at the moment of the short circuit, a massive amount of energy is released at a tiny point. The temperature will soar to hundreds of degrees in a few milliseconds. Everyone, the melting point of metallic lithium is only 180 C. The high temperature will instantly melt the metallic lithium at the anode into a liquid state. And the reactivity of liquid metallic lithium is extremely terrifying. It will directly undergo a severe exothermic chemical reaction with the solid electrolyte, even generating extreme high temperatures to roast the cathode, causing the cathode material to collapse, releasing oxygen and triggering a chain reaction explosion. This is why, under extreme abusive testing, solid-state batteries still carrying the risk of catching fire or even exploding. This is the most extreme engineering solution challenges that engineers must face. In order to defeat this ultimate boss, engineers have exhausted ways beyond imagination. For example, on the surface of the solid electrolyte, plating an aluminum oxide coating that is only a few nanometers thick to fill all the microcracks, or designing an anode with a 3D stereoscopic porous architecture so that lithium metal has enough space to deposit evenly and release internal stress. Engineers must, even on the outside of the battery, design an extremely robust mechanical pressurization device throughout the entire life cycle of the battery. Apply huge external pressure of up to several megapascals MPa to the battery, forcefully pressing back the lithium dendrites trying to poke their heads out. This showcases the purest, most hardcore engineering charm. Having said this much, let's pull the technology back to reality and do an industry trend and philosophical summary. The current market practice situation is because the interface issues and dendrite problems of all solid-state batteries are just too difficult to resolve. So the so-called solid-state battery cars are currently on the market are actually, for the most part, semi-solid-state batteries or solid-liquid hybrid batteries. Engineers have compromised inside the solid electrolyte. They secretly added a little bit of liquid electrolyte for lubrication to solve the problem of poor solid-solid contact. This is a mixed architecture. It is a transitional period towards all solid state. Although the safety is much better than pure liquids, it still hasn't reached absolute safety in the true sense. Looking back, how should we view this technology? Please remember this sentence. Engineering design has never had absolute right or wrong, nor are there perfect materials. There is only the most suitable, best compromise and choice for the current temporal context and physical constraints. Solid-state batteries are not magic. They cannot defy the laws of thermodynamics. They do indeed push the safety boundaries of batteries outward significantly. But as long as we are still pursuing compressing immense chemical energy into a small little box, risks will always exist. We are not trying to eliminate all risks, but rather to use extreme engineering means to control the risks within an acceptable range for humanity. This is the true romance of hardcore technology. Alright, that's it for today's hardcore science popularization. Actually, when we just talked about the interfacial impedance of solid-state batteries, there is an even more profound, that would make all battery engineers' heads split with pain, a microphysical phenomenon called the space charge layer. When different solid materials come into contact, ions will undergo a massive migration due to differences in chemical potential, resulting in a dead zone at the interface that cannot conduct electricity at all. Exactly how difficult is this thing to deal with? And how are the sulfide route and the oxide route in the current industry chain fighting each other to solve this problem? If you are interested in these deeper technical details, feel free to smash the bowl in the comments section to tell me you want to see a comprehensive analysis of the space charge layer. If it accumulates over a certain number, we'll tackle this hardcore topic to the end in the next video. If you feel today's content is hardcore and satisfying enough, and has subverted your traditional understanding of solid-state batteries, don't forget to like and subscribe, and share the video with those friends who still blindly believe that solid-state batteries will absolutely not burn. See you next time!